last contest. The team that solved the most problems was the Y. Who was Y? No Y. Okay, nonetheless, they did 8 problems in 1,300 minutes. Penalty. Were there any of these problems people wanted to talk about? Does anyone know how to solve H? Is there anyone in this room that knows how to solve H? Because I know every problem did get solved by a team. So this much I did notice. But do we have any H solvers here? They may be good enough they don't come to my lecture. Okay? Any other questions or any other, yes? Program Z. Z to me means Z. K. J. Okay, J. Make square. Did anybody get problem J done?
I can tell the solution. I haven't solved it yet, but
Okay, if you want to, you may do as you wish. Okay. Remind us what the problem was. I know this is ancient history now because you guys, it's more than 24 hours old.
Okay, so problem J was perfect square, so they gave you an array of numbers, which would be 3, 21, 24, something. And they told you a set of queries, so they would say from 1 to 2, 1 to 2, 3, something like that, 1 to 3. And they said that you could do an operation on a number that you could divide or multiply by a prime number. And the goal was that after choosing 2 numbers, I and j, and applying these operations and multiplying the numbers, you would get a perfect square, right? Everybody got the problem statement? Okay,
right.
Super. So I guess the first observation you would make is you could break these numbers into prime, and a perfect square with primes would look like that. Every prime prime exponent, this would be 3, this would be 3 and 7, this would be, I guess let's change it to 16. This would be 2 and 4. So every exponent would equal, it would be an even number. So a solution for 1 and 2 would be maybe combining this 2 and then multiplying or dividing by 7, whichever you prefer, right? So after you make that small observation that's pretty obvious, you could say how many primes are there or how many odd primes. You can make the observation that this is basically 0 because this has basically 0 primes because it's even, yeah, it's even, so it's already a square. And you can also make the observation that how many odd primes would a number have. So the number of odd numbers a number would have maximally would be if you multiply, if it had one of each of the smallest primes. So if it had 1, 2 times 1, 3 times 1, 4, 5, so on, right? And we want this to be less than the biggest number they gave you that was 5e6, right? So if you multiply primes until you got the biggest prime, the biggest prime made out of small primes, then you would get that at most each number could have 7 primes, 7 distinct primes. So this is something we can look to work into our solution by getting every prime factorization and only keeping the even primes. And then we can, the odd primes, exponents, and only like combining those prime exponents to get like numbers that represent the number. Like we could like do all the combinations basically. Because there are only 7 primes, 2 to the 7 is smallish, it's about less than 256, I think it's 128. So there's like a constant time, so you could do all the combinations of the prime factorizations, and the idea now is how do we use this to solve these queries? So an idea you might have is like saying, I want to know what's the best solution to my right. This sort of works, but there's a few quirks. Like the first quirk is that you might have a good solution for, like this is probably the best solution to your right for like one of your combinations, but not for all your combinations, right? So you have to go through all your combinations and say like, what's my best solution to my right for each combination? And this will fall like into that you have an array of all the numbers, like what's your max number, times what is the possible solutions. And if you see, we only have 7 distinct primes. So the best solution would be that you remove all the primes from one number and put them into the other number. So this can be like this max, we'll call it. And this can be like the 7 possible primes you can remove from each number, right? And the answer for each number would be in a range of 14, because it's like if you remove all the primes from one number and removed all the primes from another number, you would get. So now the idea is pretty simple. With this, you can get like the best number to the right with a given solution, right? And for each solution, this is also pretty small, so you can iterate it and find like 14 best numbers to the right. Now the problem like is reduced to you have an L and an R. You have queries and you want to know like which is the best solution that has an L and an R that's completely contained, right? And see if you see that, but let's continue. So that is a classic problem that you can solve with segment tree. You basically have a segment tree, and in each node you think of it as the left value, and you record what is the best solution for each of these 14 answers. You run a segment tree for each of these 14, and you say like, what's the best solution to my right? And the query is, you have an L and an R, and you want to see if any of the elements finishes before the R you put, right? And if that's true, then you have a solution in that, like in this query. And if that's false, you don't have a solution in this number. You go a number up and see if you have a solution that's worse, but still in the range. And that's it.
Okay, great, thank you. Okay. Okay, any other question that people need answered? Okay, yes.
I would like to see the solution for the problem of letter I, pet, hashtag.
Letter I was petter pound. Do we have anyone who solved problem I? Okay, you want to come up and tell us about it? Apparently this is for television, the microphone. I know you guys can't hear any louder, but try that.
All right, I'll try.
You don't need to use the microphone. You don't need to use the microphone.
You don't?
No.
Okay.
So this was the problem where you had like a string and then 2 more strings. And then you wanted to find the amount of substrings that started with the second. So like I have string S. So then I'll have like string, two more strings, and he wants to know the amount of substring from this one, such that it begins with this and ends with this. And it's just that, it doesn't matter what's in the middle, and they can be intersecting. So like, this would still be a valid way to look at it. So, going to this one, you can see that this is, I think, quite similar to the example they give. You see that there's like 1, 2, 3, I think you wanted distinct substrings.
Distinct substrings.
So it's 3, the answer, or else you would count a bunch of repeated. So if you do it the greedy way, it's gonna be n cubed, I think. And for this problem, n cubed ends up being too much because the length of the string goes up to like 2,000. So what you need to do is you can maintain the n squared solution of going through every substring, but then you need to find a quicker way to compare the substrings to these two here. So the quickest way is hashing. So Professor here talked about having caps. So that's what we're gonna use. So want me to explain a little bit of how the hashing works, or?
Could you please?
Okay. So hashing. I like to think hashing as viewing the number as a polynomial of greater size. So let's get the substring. AB. I can think of it as a number that's like the value of A times a variable X. So it's going to be an increasing polynomial. It'll be like this. I'll make it the other way around, so it'll be like this.
Right, so he's using it looks like now the exact same hash function that I used, correct?
Yeah. It's always like this. Like, it's always based on like forming a polynomial from it. Can you see it, or did I write it too small? So you can think of representing this as a number built like this. So x will be a base, and you can see that the number will be very big very quickly because of the exponent. So usually you do it modulo something. It's not really good to do it with unsigned long, as it's really easy to hack it. And we usually choose a prime base that's larger than the value, than the largest value that you're gonna multiply as a coefficient. So usually you can use like 313, or you can like generate a random prime every time you do it. So so we have our string here, and we now want to compare it to these. So what can I do? I want to compare A to the beginning and B to the end. So what do I know? I know how the what's the exponent of the variables and like from the beginning. So from the string that I want to compare, I can already put it like this. So let's say the string was just AB and this second was BA. So this string here, if I represent it just the way I did it like this, it's going to be A times X plus B. And you see that it's like quite similar to this one. So you need to multiply by the offset, or yeah, you can multiply by the offset to get here, or you can do it the other way around to subtract and then divide to get to here. So it's up to you. I think in this case it's a bit easier to like just grab this side and then get this and multiply it by x squared. It will be the offset because the length is 2 less. And then you'll see that we'll get like pretty much the same thing. So if we compare the numbers of these two, we'll get the same number. So like it'll actually be a valid answer. And so we do the same thing for BA. But BA is already in the beginning, so I don't need to worry about that. So like, if I get BA, it'll be B times X plus A. And you can see that they don't match the numbers. The expression itself doesn't match, so there won't be any problem. So if I compare, if these were the two strings and this was the original string, this substring wouldn't be valid because, as you can see, the beginning and end, the beginning is the same, but the end isn't. So the beautiful thing about hashing is that all of this is done in O of 1. So it ends up being just n squared. And to check distinct substrings, you can just check if I've seen the hash already, and you pray for it to not be like repeated. So, and you can like put it in a map or whatever. So that's like the basic part. And then you just do it for every substring.
Okay.
Sorry.
Thank you, yeah. Okay, thank you. Whenever, I guess I'm supposed to put this down, and I'm supposed to still be heard on television, is that right? Okay, the one question about this problem, you guys solved it, I don't, so I don't know. Is this the kind of thing a suffix tree would in principle be a good thing for? Okay, I gather you're trying to figure out whether or not one string begins or ends with overlaps with the other one. What is the overlap? How would you tell that there is an overlap between the string starting here and the string starting here? Both of them are suffixes of the original string. You want a matching prefix of the original string. That's the kind of thing that would be captured by the common part of the path till those two suffixes diverged, okay? Or that least common ancestor that I kind of mumbled a little bit about, okay? So if you could build a suffix tree quickly enough, okay, this would be a way, that might have been a way of doing this, okay? I don't know about the specifics of it, but the people see that where the suffix tree thing comes in a little bit, okay? Any questions? And one thing I talked about in my slides that day, which I never got to talk about here, was something called a suffix array. And you can look at my slides if you want, or if I run out of interesting material, maybe I'll go back to it. But, yes?
Yeah, you can solve it with like two suffix arrays, one with the original string and one with it reversed. And then
Okay, so he's saying that I could solve this with a suffix array on a string and its reverse, which is a common trick that we saw for dealing with prefixes and suffixes. Suffix trees, I told you how to build them incrementally, but they might be slow, okay, if you built it the way that I told you. There's fancier linear algorithms. But suffix arrays are probably easier to build, okay, if I were, in a contest where you had to write something very, very quickly. Suffix arrays give you a lot of what suffix trees do, okay? And they're relatively easy to build. And they're relatively easy to understand. So if I don't get back to that subject, don't be afraid to look at it either on my notes or Gus Field's book. Any questions? Okay, so what I'd like to talk about today, just because it's what I'm hoping the contest will largely be about, is computational geometry. And I will claim that there's two aspects to computational geometry. There is the boring aspect and the interesting aspect. The boring aspect is the fact that programming geometry tends to involve, there's a bunch of, I will say, details or tricks or complications that come up with doing elementary geometry programming. And this is stuff I'm going to try to talk about relatively quickly, because if you've seen it, it's boring. If you haven't seen it, it's probably also boring, okay? But it's important to understand. Then I'll spend the second part of my talk, I'll try to talk about more interesting algorithmic aspects of geometry. So that's kind of my plan. And I've been told that, you know, the beginnings of my lectures are always boring and slow, okay, then the better stuff is at the end. I'll try to make the beginning part a little bit faster. But still, I want people to make sure people understand these things. Okay, so one of the things that makes geometry very hard when you're programming is geometry has a lot of special cases, okay? In that normally when you're trying to, so there's, you know, usually if you have a set of lines, every line intersects each other at this one point, okay? And it's common when you're programming things, the natural way to assume is that there are no places where there are if you're dealing with a problem on lines, where all lines go through a single point. Or deal with 3 lines, all of which are, or deal with 3 points, all of which are on the same line. Or think about parallel lines. Every pair of lines intersect except parallel lines. They don't, those are weird, okay? And dealing with these special cases is one of the things that makes doing the elementary programming in geometry hard, okay? And so I assume all of you have done, is there anyone here who has not done some geometry programming? Assume all of you guys to have gotten here, you've done plenty of this stuff. But this is, I still think, a big problem. Now, there are different techniques for dealing with this degeneracy to make things simpler. One way, which I like to use, which I didn't talk about on the slides, and may very well not come up or be legal in the programming world. First of all, does everybody recognize the problem that I'm talking about of these special cases? Okay? Now, one way that if I were doing something, might try to solve special cases is randomly perturbing the points. There's different techniques for this thing. What happens if you take suppose let's say you have a geometry problem where they give you an error tolerance. You have to get the answer to within this, okay? And you're fearful about degeneracy. You're fearful that they put all the points on a line and you're gonna get. What happens if you move each point in a random direction a little bit, okay? What happens if you have points that are all on a line and you move some of the points randomly you randomly pick a direction to go and you move the point a bit? Are there going to be any that 3 points on the same line? Almost certainly not. Do people get that idea? So one way to break degeneracy problems that may or may not be relevant in what you guys do is just random perturbation. You change the point sets by a little, you hope that you can change it by a little enough to break any troubles they give you, okay, while still while not ruining the answer very much, okay? What other things do they do are approaches to try to deal with this kind of degeneracy? Well, one thing the program setters probably do, how often when they give you geometry problems do they ask you to work on integer numbers, integer points, rather than all the time, okay? And one reason for doing that is that kind of, again, there's special degrees of it makes it in some ways easier to handle some of these problems, okay? But anyway, this is what you got to be aware of, that there are weird degeneracies, and that kind of comes in. Okay, when you're representing a line in a program, how do you represent the formula for a line? A line that goes through 2 points in the plane, right? I was taught in geometry that you were supposed to use the form y equals mx plus b, okay? The question is every line of the form y equals mx plus b? The answer is no. What line is not of the form y equals mx plus b?
Straight line.
It is no, but all lines are straight.
Yeah, okay.
So it's not a straight line, but it's just a line where the line of the form x equals 2. If you have a line of the form x equals 2, m is 1. What is the intercept? I guess minus 2, but you desperately want a zero coefficient in front of the y, okay? So is there a more general view of a line? Okay, when I was writing my programming challenges book, I did it in terms of lines of the form ax plus by plus c equals 0. Now it handles the special case as the case where a equals 1. And so either a equals 1 or a equals 0, and now I can represent all lines. Any questions about that? Do people do things this way, or am I doing it wrong? Who does it this way? Small number of people. Who doesn't do it this way? People in the back, you guys can decide if the people in the back are better or worse than the people in the front, okay? Obviously, this is in some sense only one special case. If this is not a problem on your problem, don't do it that way, okay? Any questions? And again, I'm gonna try not, I have on my notes the code from my programming challenges book. Okay. What else is there? When you have lines, you worry about the point of intersection. Again, as we said, is there a point of intersection? Well, unless the slopes are parallel, okay? And I believe that using, again, if you want to find the point of intersection, this I know you have done in geometry. It's a point that has to be on both lines. So you can set the two lines equal to determine the y coordinate and then solve for the remaining x coordinate. So finding an intersection point between the two lines isn't hard, okay? Again, tricky sometimes if one of the lines is parallel, is straight up, one of the lines is horizontal, you've got to handle all of those special cases, and that's what makes this stuff a little bit tricky. Okay? When you're dealing with geometry programming, you've got to deal with angles. Again, when I was growing up, angles were from 0 to 360 degrees. I assume you guys now live in a world where angles go from 0 to 2 pi. Yeah. Is that correct? Okay. So, this is better to work with. Okay. And if you want to try to find the angle between two lines. Again, there's presumably a simple formula using the tangent, but again, if one of the lines is, I guess this is a vertical line. A vertical line would be trouble, okay, or is a special case. And so if you look at the formulas I use in here, they're general for both, for all lines, including the case where of the form x equals some constant. Okay. What else do we need to know? We need to know about perpendicular lines and how they cross. We say that two lines are perpendicular if they cross at right angles. And again, I think you guys know that basic formula there. The perpendicular line to one line y equals mx plus b is we invert and negate the slope, and that will give it to us. Any questions about this? This I know is pretty simple. How do we find the closest point to a line? This is again simple, but actually will be maybe useful if we get to Voronoi diagrams. How do we find which point on a line is closest to this? We know that it goes through the perpendicular, we find the perpendicular line that goes through this thing. If we have this line over here, we know its slope. We know that these angles are right angles, means that we can use minus 1 over the slope to give us the slope of the perpendicular line. Once you have a point, and once you have the line that you want, the slope and a line through, a point on that line. That line is fully determined. Now you've got two lines, what you really just want to find is the point of intersection between those two lines. And that is the closest point between those two. Any questions? This again, I assume everybody learned probably in high school better than me. Okay, what is good about it? Another sort of basic thing that comes up in geometry a lot are triangles. What do we know about triangles? We know that the sum of their angles on the inside add up to pi. We know that if we have a right triangle, it observes the Pythagorean theorem. So this is, a squared plus b squared equals c squared. This is a, this is b, this is c. If it's a right triangle, a squared plus b squared equals c squared. And that helps you reconstruct. If you know the angles, you can reconstruct sides. This is a classic thing in programming problems. Any questions? How many people here know about distance metrics that are not Euclidean? In fact, I'm pretty sure people have heard about this thing. You know, to measure the distance between points. Typically, what is the formula people use? You're used to seeing that it's sort of delta x squared plus delta y squared, the square root of, that's usually the distance between 2 points. Now, there's a more general class of distance metrics where we replace the squared by a k, raise it to the kth power, and we raise this thing to the 1 over kth power. This thing is a distance metric in the sense it has all the same real properties of distance that we like it to be. This is more general. How many people have seen this distance formulations? A few, very few it seems, okay? Sometimes it's interesting to look at this. Does everybody agree that your standard Euclidean distance is when k equals 2? This you understand. Now, are there other special values of k for which this is true? Is interesting. What happens if k equals 1? Okay? If k equals 1, then you're summing the differences. Okay? I guess you take the let's take the absolute value of these differences. The goal is not to worry about negative values. Okay? This basically, for k equals 1, it's going to take the differences of each dimension, raise it to the 1th power, which leaves it the same, and then takes the 1th root, so it leaves it the same. What distance does this correspond to? San Paulo distance, right? You have a grid of cities, okay? How long does it take to walk from here to there, okay? It's the change in the y plus the change in the x, okay? Does everybody see that? What happens if you take, for any value of k, this will give you a reasonable distance metric that has the properties of distance that you would like. I actually almost listed them on a slide, but does anyone know why we live in a world where k equals 2? Actually, what is k equals infinity, just to double check that? What is the effect if we take the change in the x, raise it to the infinitieth power, or some huge number, change the y difference, raise it to a huge power, and then take the infinitieth root for some value of infinity? What do we get?
Distance. Chebyshev distance.
You say Chebyshev distance? That might tell Chebyshev something. What the maximum of them? This is going to give you as the distance the maximum difference. So what would be the so-called now Chebyshev distance, or I think of it as the L infinity norm distance. What's the L infinity distance between this place that's 3 blocks from here to this place that, as you can tell, is 4 blocks from there? 4 is bigger than 3. When you raise 4 to the infinitieth, it's much bigger than when you raise 3 to the infinitieth. Does everybody see that? So it's the dominant, and then this term is going to be so much bigger to leave the other one in the dust. And then when you take the infinitieth root, it will work out that the distance from here to here is going to be the distance of the maximum coordinate. Okay? Any questions? Sometimes this is useful often when you're looking at distances of points in data. Okay, it may be interesting in programming contests. But why do we live in a world where k equals 2? That's, I guess, what I'm curious about.
It's rotation invariant.
What?
It's rotation invariant.
You say it's rotation invariant? That may be a good reason. I think we just like the Pythagorean theorem. The Pythagorean theorem holds for distances in a world where Euclidean distance is true. Okay, maybe Euclid and Pythagoras were friends. Okay? Any questions about that? Okay? Fine. But so there are triangles. What's the important thing to know about triangles is that when you bring trigonometry into things, okay, given various sets of angles and sides, you can reconstruct the other thing. Any question? I do one question for you guys now that I've got you here. You probably at some point had to learn that cosine of an angle was the adjacent side over the hypotenuse. And you had to learn that the sine of an angle was the opposite. So again, if we have a theta here we have a theta, there is a hypotenuse, which was the longest edge. There was an opposite side, and then the other one was the adjacent side. Were there any things you guys used to remember what the formula for cosine was and sine versus not sine? What is there in the United States, there's a memory trick, which we somehow imagine that there's an American Indian chief whose name was So-Ka-Toa, and that's how I remembered what those relations were. That probably did not work in Portuguese. Is there any rule that you guys learned for this?
It works in Portuguese.
What?
It works in Portuguese.
It works in Portuguese, okay? So anyway, if you haven't learned this yet, you probably didn't get to this point, but if you did, remember that. Okay, one other primitive that is used a lot that is important in, basic programming geometry is to compute the area of a triangle. And, there's various ways of doing this when you were taking elementary geometry. But there's an interesting way to do it using linear algebra, which I don't know if how many people know this way of computing the area of a triangle with a determinant? And how many people don't? Okay, a few will admit to it. So what is interesting here? There is one interesting way to compute if you have a triangle in 2 dimensions, what do you have? You have a world where you have 3 points with 2 coordinates. We can make a 3 by 3, a 3 by 3 matrix where we consider the x and y of the 3 points, with the third dimension being equal to 1. If you multiply out the determinant, you get this expression. What's interesting about this thing? Well, the determinant is going to be twice the value of the area of this triangle. Okay? That's kind of interesting. Okay? But it's actually not just the area. But if you notice, you've got negative terms here. And depending upon the order of those 3 points, the area by the determinants will either be positive or negative. Okay, so this is really a way of getting something called a signed area. And this signed area is going to be very, very interesting. Okay, because if you think about it on a triangle is 3 points. Okay. There is, in terms of area, no difference between a triangle that goes from A to B to C, from one that goes from A to C to B. But in terms of signed area, there is. There's a question of whether or not it's clockwise around or counterclockwise around. Okay? And this formula makes that distinction. And that distinction is going to be useful to us for a couple of different reasons. Okay? One thing is, it gives us a way to tell the difference between whether something is going around clockwise or counterclockwise. Okay? So if there's a difference between ACB and ABC, if that's the sign, that's to tell us whether or not the points are going around clockwise or counterclockwise. So this kind of an idea gives you a way of telling that. Okay? It gives you a way to tell, by the way, to compute the area, the signed area of things in higher dimensions. The simplest thing you can build in 2 dimensions is a triangle. The simplest thing you can build in 3 dimensions is a tetrahedra. Okay? The simplest thing you can build in 4 dimensions is a 4-simplex, whatever that means. Okay? I can't see very well in high dimensions. But it should be clear that there is going to be a generalization of this. And what's great about this determinant formula is it generalizes to a notion that d factorial times, the area, the volume of our simplex is going to be the determinant of the d points that we have, each of which is going to be in d minus 1 dimensions. Okay? And so we pad the last column with the 1s. Any questions about this? So this is a useful thing. How can we use this to tell whether 3 points are on a line? When the determinant equals to 0, that means that they're on the same line. Okay? Any questions about that? So this is a useful primitive. Okay? What do we know about circles? Circles you may think of as being something that is round. Okay? Well, actually, circles are only round if you believe in Euclidean distance. Does everybody see that? What is a circle? A circle is a set of points that are a distance of 1 from you. Okay? You have a center and you've got a radius. What does a circle look like in Manhattan? If any of you ever come to New York? Okay, I think a circle that in New York is going to look like this. Does everybody see this? Okay, here it's 1 unit down here. Okay, to get to this point, it's halfway down and halfway over. That's also 1. So if we're summing up the distance, this is what a circle looks like in Manhattan. Okay? I encourage you to visit New York and see if that's what our circles look like. Okay? Any questions about that? Okay? And I don't think we need more about basics on circles than that. Let's say probably not. Okay, now what is the difference between computational geometry and what I'll call real geometry? Computational geometry, real geometry tends to deal with lines, infinite lines. Computational geometry is typically the study of polygons and things like that, where you have objects made from line segments. Okay? And one of the main primitives, every line can be represented by slope and intercept. Every line goes through 2 points. Every line segment has a starting and ending point. Okay, and that's kind of the natural way I represent a line segment. Okay? And, anyway, let's not go through that. To test whether 2 line segments intersect is, again, in some sense, it would seem like a trivial matter. Okay? because again, if there are two lines, they intersect at a point. Either if you have if this is one of your line segments and this is the other line segment, either that point of intersection is in the line segment or it isn't. Computing this point of intersection gets tricky in the special degenerate cases. If you're interested in, again, how I did it to deal with degeneracy, this was my line segment intersection testing. Any questions? And this I know is still the boring part. It was actually, okay, let's just say boring part, and we won't go through that. Okay, what else of boring part do we have? We want to know something about polygons. Polygons are closed chains of line segments. You can implicitly represent a polygon by just listing the vertices in order, okay? And where there's an implicit edge between vertex I and vertex J, and that's a useful thing. A specific class of polygons that are going to be important to us are convex polygons. When is a polygon convex? This is a convex polygon. What makes it convex? What does convex mean here?
No angles over 180 degrees.
One way to think about it is that none of the internal angles goes over, I thought you guys learned about radians. So over pi radians, okay? If none of the internal angles go over pi radians, that's a definition of a convex thing. Here's a non-convex polygon. What is a property that makes a convex polygon interesting?
The segment between points in the polygon.
One said is that if you have one point that's in the polygon and one point that's outside the polygon, the entire segment is in the polygon. That's not true for our non-convex polygon, right? Okay. So how do we test if something is convex? Well, you could do it by basically testing whether or not all the internal angles are greater than, are less than pi radians. Another way, though, the way that I would want to do that is with my test for signed area. My signed area will tell me whether or not my angles are going clockwise as I walk around something. What is true if I start walking in this direction? This is going to be this is going to be convex if every step along the way my angles are, in this case, clockwise. If I walk from here around it, if every angle is if every rotation to the next point is clockwise, then it is convex, okay? And so using this basic primitive to tell whether or not something is clockwise or counterclockwise helps me tell if things are convex. And the predicate for that is based on my sine triangle area. Any questions? Okay, any questions? That is the end of the explicitly boring part of this class. Okay, if you just to do it, and now we can maybe get on to the algorithmic part. Any questions so far about the primitives? Okay, so in computational geometry, to design computational geometry algorithms, I am going to say that there are a few different ways to look at it. There's some classic problems it's good to know about, and there's some techniques that are useful to try to design new algorithms. And I'm going to try to talk about both of these, okay, today. The most first, let's say, interesting problem in computational geometry is something called convex hull. Convex hull is what the is the smallest convex hull polygon that contains every element of a point set. Okay, And it's good for giving you a gross shape of what points are. That's why convex hull is kind of important. How do you guys compute convex hull? This much I think I'm going to know the answer to. How do you compute the convex hull? What is the algorithm that you use?
Monotone chain.
What?
Monotone chain.
Monotone chains. Okay. It's not the answer I was expecting. What? Gram scan is the algorithm that I was expecting. How many people even know what gram scan is? Some, but not all, actually. Okay. How many people don't know what it is? Or is it? So I see some people twitching. Okay. So what is this? There is a way to. How do you actually compute the convex hull, the smallest polygon that contains a bunch of points? The gram scan algorithm is an algorithm that starts by finding a point on the hull that has to be on the convex hull. Suppose I give you a bunch of points. You know, bop, 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 bop. What points do we know have to be on the convex hull? Have to be on the outside of the smallest convex polygon that we do. If I quickly said, find me a point that was on there, which points have to be on there?
Leftmost.
The leftmost point, which in this case happens to be this one. Is there any other one that happens to be on the has to be on the hull? The rightmost one, no reason to be prejudiced left or right. Is there any other ones that have to be on there?
Lowest one.
The top and the bottom points clearly have to be on there. So finding a box around the points is actually quite easy, okay? And know that everybody's in the box. The box is convex, but the box is not the smallest such polygon, right? What did the gram scan algorithm do? The gram scan algorithm, algorithm, what did it do? Okay, it started by, I think I discovered I have this, right? Okay. It starts from one point that's on the hull. It sorts all the points from, according to their angle around each point. Okay, so we know if we have the lowest point that we're starting with, what are the angles that are made by every one of the other points? What do we know about the angles of every other point, okay, that we make? It's got to be between what? 0 and pi, not 2 pi, but pi. Good. We can sort the points according to what the angle is, okay? And that gives us an order of the points, 1, 2, 3, 4, 5, 6. We want to try to find the outer wrapper of those points. That's what the convex hull is. How do we do this? What we're going to do is one by one insert the points into the hull. In this case, what happens? 0 and 1, and the next point, we've got 3 points on a triangle. Is a triangle convex? So what we have so far is always convex, okay? Now what happens when we add a 4th point? Is adding 0.3. If we add 0.3 to the triangle we have so far, is that set of 4 points still convex?
Yes.
How do you tell if it's convex? What do you need? What is the test that you would use? Whether the angle is smaller than, internal angle is smaller than 180 degrees than pi, or more, whether it's still counterclockwise. What happens when we add the next point, 4, on there? That creates a angle, that creates a turn that is clockwise. That creates an internal angle greater than 180 than pi. What do? For the last point, because it's the one with the highest angle, has to be on the convex hull. We're now going to delete a chain of points until we get rid of all counterclockwise points. That's what deleting 3 would do. So what is the idea? We are building up a, a convex, chain. Our next point out here may very well, if we put it in here, create a point here that causes a counterclockwise angle. If we connect it here, it might also collect it. We'll delete it, and delete everything till we get a simple polygon again. I didn't explain that completely clearly, but I think many of you know. Any questions about that? Everybody's familiar with how gram scan works, right? You sort the points by angle and you incrementally insert and then delete the ones that don't do so well. What's the running time of gram scan?
Linear.
Well, it's linear. It's not linear, but you have to sort by angle, right? So if you have n points and much time does it take to sort n points? N log n, okay? So to sort n things by angle, it's n log n. The act of inserting and deleting takes a total of linear time. But this is not completely obvious. So let's respect it for a minute, if you haven't thought about this for a while. When I think of how much something costs in big O sense, I usually think of it as how many operations am I doing times what's the cost of the biggest operation. Is that how most of the time you guys think about algorithms? What about in the gram scan? Can I do one insertion of a point, which will cause, let's say I have, what would be a good example of something? Suppose I have bunk, 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 bunk. You see how I've got a chain of points bending around here? If I have n points in my data set, how many points might it get deleted when I insert a single point into my gram scan now? Does everybody see that I might have to spend order n time deleting each of these? If in fact I had n steps, each of which cost me n time to delete, this would be a quadratic thing, right? Why is this not quadratic? Okay, did everybody see what the problem is? The act of inserting the next point might cause me to spend order n time undoing things, okay? Why isn't gram scan n times n?
Insert points once and delete points once.
Okay, actually in principle it is big O of n squared. Remember, big O is an upper bound. So if I say gram scan is big O of n squared, I'm saying something's true, but I'm saying something that's not interesting. Because in fact, this part of it only takes linear total time, because every point can only be deleted once, okay? And this kind of analysis is probably the simplest example I know of an algorithmic technique called amortized analysis, where instead of trying to analyze it by the worst case times the number of times you're going to be doing this operation, takes into a fact that the only reason this deletion is going to be expensive is because all the other deletions were very cheap. You didn't delete any single point so far, okay? So the total amount of work on average for a deletion is always going to be at most constant, okay, on average. And so therefore the total is constant. Any questions? Okay, this I think you know how to do. That's my gram scan, that's fine. But let me start with something here that might be interesting. Why is it that gram scan sorts the points by angle? Has everybody here, when they were taught gram scan, were they taught that all the points, that you sort the points by angle around something? How many people saw that? Please raise your hand just so I know I'm reaching people. There's another version of what I will call, quote unquote, gram scan that sorts the points by X. And I will claim that it's the same basic idea, and I think a simpler way to think about convex hulls. What is the idea here? I'm going to have a bunch of points, okay? I'm going to sort them by X coordinate. And like the gram scan, what am I going to do? I'm going to one by one add the points in the order that they were put in, and I'm going to delete any point that is swallowed up by adding the new point as I go from left to right. Okay? So what is the idea here? Let's just start with this thing. Suppose I am going to build up a convex hull when I go from left to right. What's kind of going to happen? Here's the leftmost point. Here's the second. Here's the third. This we agree is a triangle, right? Here is the fourth. The fourth point, because it's the rightmost point, has to be on the hull. Does everybody agree? Now what happens? If we take a look at what are the points that are visible to it, okay, if we think about kind of an angle rotating around, okay, this is now going to be a convex hull that's going to have 4 points. If the next one is out here, here we're going to have to start deleting things. How do we know which points to delete? Well, the point that is rightmost, certainly you can see the point that was next to rightmost. This point was on the hull. We know which point that one is. How do we figure out whether or not we need to delete this point? Well, it's a question of, is this angle counterclockwise? Or is this angle clockwise? We're going to kind of work. The only difference here is that instead of going, doing our deletions in one direction, which is what gram scan does with the angle, we might have to delete points when we add, if our convex hull looked like this, adding 1 point, might delete the last, we'll go to the last point. We have to walk up here and walk down there, deleting points till we have it. Does everybody see how this left-right thing is kind of like a gram scan? Okay? Why do people like the angle gram scan better?
It's a little bit faster.
It's a little bit, you say faster?
Yeah.
To me, they're both doing the exact same thing. So when you say a little bit faster, I don't see the speed difference.
It's really cool.
What?
It's really cool.
It's really cool, okay? That's one difference, okay? Maybe another difference, maybe it's a little tinier bit harder to program because you've got a special case above, okay, the chain above the point versus the chain below the point, okay? But it should be clear that this is the same basic idea as, as gram scan. I find it's clearer to me what's going on, but more importantly, this is a model of what we would call a sweep line algorithm. And the sweep line algorithms are kind of the single, let's say, I'll say most common class of algorithm geometry problems in 2 dimensions, okay, where you basically are going to sort the points and then look at events as you go left to right. And I'm going to go review those in more detail later on. Any questions about convex hull or anything like that?
By the way, when I said the monotone chain,
This is what you meant. Okay, so he was being smart, okay? I think of this as being just like gram scan, okay? And seeing the connection, I think, is a useful thing. Okay, what is another sort of very, very important problem in computational geometry? Is that of finding a triangulation. What is a triangulation? It's basically, if I take a set of points, I find a convex hull of that thing, okay? That will define the shape of those points. A triangulation of a set of points is you take the convex hull and you, fill in the, connect the internal and hull points together in such a way that every face is a triangle, okay? This is a very useful operation to do, okay? To kind of take space and break it into triangles. Now you're talking about, you give, each triangle kind of is a region. The region covers the whole thing, which is useful for trying to identify what the nearest point, lots of things. How can you take a set of points and triangulate it? Okay? What's the simplest way to take a set of endpoints and triangulate it? Okay? Does anybody have any ideas how to do it? Okay? How would you triangulate these points? Let's think about this a little bit.
The first leftmost has to be in the same triangle.
What?
The first leftmost has to be in the same triangle.
The first three leftmost are going to be in a triangle. That's certainly true. Well, actually, when I say certainly true, notice that there's many, many different triangulations for a particular point set, right? So when you tell me the left three points are going to be in a triangle, what you're really saying is the left 3 points can be in a triangle. That's the right way to say that, right? How many ways, actually, are there to triangulate a convex polygon? Does anyone know this thing? If I have my points 1, 2, 3, 4, 5. Okay. That's our friend the Catalan numbers again, right? And how many what is the nth Catalan number? You say 2n factorial or that kind of thing? What you really know is it's the number of young tableaus of shape nn, right? But the point is that there's an exponential number of triangulations. So when you tell me the first 3 points can be connected in a triangle, the answer is yes. But of course, there are other triangulations where that's not true. So, okay, so let's go through this again. Can anyone give me a way, actually building on that idea, how you would construct a triangulation of a set of points? Okay, seeing a couple of hands, yeah?
Like 2 different ideas. Maybe like if you do the gram scan, first you get like a bunch of little triangles that could be in triangulation.
Okay, so one idea would be to do a gram scan. What would be a gram scan's idea? The gram scan was we sorted these things from left to right. Actually, let me make them left to right so that I know what I'm doing.
I was thinking more by angle.
Well, they sorted them by angular order around this, right? And so you're saying ka-chunk, ka-chunk, ka-chunk,
Yeah.
ka-chunk, 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 ka-chunk.
Yeah.
And if I add all of these things,
Yeah.
it's a triangle. Does everybody see that?
Yeah.
Is that a triangulation of the convex hull?
Not yet.
Not yet. Does everybody see that? How would you go about building this triangulation? Okay? Any other idea?
Like in the places where you would remove points, you add another.
You're now trying to do maybe I do some surgery over there.
Yes.
Okay? What about instead we use my version of gram scan or his version of monotone whatever? Okay? What is going to happen now? I start with 1 point on the triangle. You have said you're right. These 3 form a triangle, right? I'm going to insert another point. What am I going to do? I'll make this, but what if I don't delete that triangle, right? Now comes the more interesting case. What should I do with a point now that's going to swallow up some other points? how do I make this incrementally to be a triangulation?
You can make two triangles.
Instead of swallowing it, why don't I just add edges to all of these things? Does everybody now kind of see this? Here I'm gonna put this. Now I'm gonna go ka-chunk, ka-chunk. Out here, ka-chunk, ka-chunk, okay? So by modifying by adding chords to these things, instead of deleting them, I claim that is one way an easy way I can make a triangulation from this. Any questions about that? Okay, so triangulations are good things, okay? And that is the easiest way I know to triangulate a point set. If we get far enough today, there's other ways of triangulating point sets which are important. But this is, I think, an easy thing to see. Any questions? Now, has everybody ever seen, something that I would imagine has appeared on Contest for You, though, is given a polygon, triangulate a polygon. How many people have had that on a problem they've done? Not as many as I thought. Okay, that's surprising. Suppose, let's say, instead of a point set, I give you a polygon. Okay? A polygon, remember, was, you had vertices, they were connected in a chain. Let's put this like here. How do we triangulate the region inside this polygon? That's a common thing to do. Remember, before I was talking about just taking the points. I claim it's kind of easier and often common that you'd like to divide the internals of a polygon into triangles, right? How do you do this? How can you triangulate the inside of a polygon? What do we have to do in order to do that? We need to be able to find chords. That actually gets back to the same thing with our Catalan number-like idea. A chord is going to come in and divide the polygon into two things. Now, does everybody see that if we have a set of points like this, our polygon can be considered numbered in some kind of order, 7, 8, 9, okay? Can we add a chord between any pair of points?
No.
No, why not?
To the outside.
Well, first of all, there's a problem that it might be outside, okay? Second, which is maybe a little bit related to it, you could imagine a case of something where maybe your polygon looks like, let's say, I want to say, ka-chunk, ka-chunk. Now, this is still going inside, but it might conceivably cut through some other piece that's already there, right? So how do we go and cut through, how do we triangulate the inside of a polygon? Does everybody see that if we can add chords so long as they are inside and they don't cut anything else, right? Okay. So what would be a way to think about it, okay? The algorithm that I like best is something called Van Gogh's algorithm, okay? And what is the idea? We are going to look for trying every pair, try to add our chords such that we are adding chords between basically neighboring points. Does everybody see that between 2 and 3 and 4, you can add a chord and it's okay? Okay? Now, what do I know? If this angle over here is, less than 180 degrees, that's gonna handle the case that the chord is completely outside the angle. So if I look at this angle and it's greater than 180 degrees, I can't add that chord, right? The other case I have to do is to make sure that there's nothing else in this box, this triangle, that would have caused trouble, right? And that's what, how would I test if this is the case? In the case like this, where a branch of the object kind of goes into this triangle, that is marked by there being an internal point in that triangle. Does everybody see that? So how much time does it take, given a triangle and another point, to tell whether that point is inside that triangle? Better be constant, because there's only 3 things and another thing, 4 things, right? But does everybody see that there's a point that if you can test whether or not a point is in what you call it? A point is in a triangle. Does everybody see that you can now go and test whether that triple is okay, is empty? So what are we going to do? We're going to look for every convex angle, test whether or not it is empty, right? And how are we going to test whether it's empty? Well, we could try all other end vertices one by one and say, are you in there? Are you in there? Are you in there? Okay? And if nothing's in there, we call a part of a polygon where it's 3 consecutive vertices that are empty. We call that an ear, okay? And if you look at a polygon, if we look at the one I've got on the screen, this here is an ear. See that? This here is an ear. I guess this would have been an ear also, right? So every polygon, it can be proven, always has at least 2 ears. And so therefore you can find one of these things, cut it off. Once you cut off that ear by adding a chord, now you may create ears over here and over here, okay? And that you then got to test it. So then basically what do? You identify the earness of every vertex on the polygon. Then you add a chord between an ear and see if you create any more ears, and keep doing it until we get a polygon, triangulation. Any questions? Yes?
Is the complexity unsquared because you have to check that no our point is inside the triangle?
So the good thing is I have triangulated this polygon. The bad thing is this is going to be n squared, okay? At least as I've done it now, it's going to be n squared. Because for every potential ear candidate, I'm checking all of the points in them, right? Now, you might imagine you can change it a little bit. Once a point has been proven to lie within this ear, this triangle, it's not going to lie behind in anybody else's ear. So maybe there's some optimization, but that's not important. It's going to be quadratic. Any questions? So what's interesting? There's 2 interesting things I wanted to maybe leave you with, okay? One is to note that there is if you have a polygon, or in fact in any triangulation, let's come back here. In any triangulation, okay, you have a triangulation of a polygon. You have the property that you're going to have chords coming in, and that every triangle is going to have neighbors, okay? The dual tree of a polygon, which is what we have here, we have a vertex. The dual graph for a triangulation is for every triangle we have a vertex, a point inside the triangle. And we connect it to triangles either way, that border it. So this point up here, this node is of degree 3 because this triangle, okay, borders on 3 other triangles. What's the highest possible degree of a node in this tree? 3. Why can't a triangle be connected to 4 other triangles? Because it's a triangle. Tri is 3. There's only 3 sides that it can be connected on, right? So one interesting property is that the dual graph of this of a polygon triangulation is always a tree. The other question is, does anyone know why this is called Van Gogh's algorithm? Okay.
We should delete.
What?
You're cutting ears.
Cut his ear off, right? That's what this algorithm is doing, is repeatedly cutting off ears. And Van Gogh did that, and it wasn't a good idea, so I don't recommend it. Okay, any questions on triangulations? Okay, is the coffee ready or? Well, let me give you one more thing, I guess, just to double check this. Suppose you have a polygon. Why would you want to triangulate a polygon? Okay. One reason I will claim you want to triangulate a polygon is to compute the area of it. What is the area of this polygon? It feels complicated to compute because it's got all these, bumps and bridges and stuff like that. The area of a triangle is very easy to compute. Remember we talked about signed area? We talked about how you use the determinant to compute a signed area. Well, given a triangulation of a polygon, what you could do is the area of the polygon is going to be the sum of the areas of every triangle, okay, that you make in a triangulation, okay? So the simplest, one reason to triangulate polygons is to compute area, okay? Any questions about that? It turns out there is a slicker way to compute the area of a polygon using signed area, okay? Because remember, the area of the signed area thing is both positive and negative. Somehow there is this magic formula that basically, given a, that computes the area of a polygon by adding up the signed areas, okay, in an interesting way, and the signed area is offset. But to me, the simpler way to do it is to triangulate it and just add the absolute areas inside, rather than take the convex hull and use the signed areas to subtract off what isn't there. Okay? Any questions about that? Okay, at this point, I'm willing to let you guys have, is coffee ready now? It's supposed to be ready at 10. Okay, then go have coffee and we will continue with geometry. problem that I think is probably a programming contest level problem. That I don't know if you've seen one of these. We know that people are complex, but are people convex? People are not convex. Does everybody see? If you look at the screen, we have got a polygon that represents a person. It is not convex, right? So one problem that you might consider is a problem of given a polygon, how do you cut it into the smallest number of convex pieces? Okay? Does everybody see that if you want to make a person convex, I'm showing you exactly where you got to cut them in order to leave them in convex pieces. Okay? I guess that's maybe one thing that Van Gogh was doing, okay, was striving for convexity. How do you find the smallest number of pieces that a polygon would, what would be an approach to try to think about this? Let's think about it. How do you carve a polygon into a smallest number of convex pieces? Okay?
The ones that make the maximum possible area.
No, so we want the smallest number of pieces such that each piece is convex. Okay, you see what's happening? If you cut off my head, which I don't recommend, my head is convex, okay? If you cut off my leg may be convex, but the leg's attached to me, obviously 2 legs. It's easy to draw a point outside. Points that are in my body that cut it aren't within there. How would you take a polygon and cut it up? First of all, how would you take a polygon to cut it into pieces so every piece is convex? Let's try this simple. All I demand is every piece is convex. How do we do that? What would be a simple way to do that?
You know that for each angle that's more than 180 degrees, you have to cut it there.
Okay, simpler thing. What if I just want what is the simplest way if I want every piece to be convex?
Triangulate.
Triangulate it. If I take my polygon and triangulate it, every piece is a triangle, every piece is convex. Okay? So what is interesting? What if I want to find the smallest number of convex pieces? How many triangles that's a good question. How many triangles will I have if I have an n vertex polygon? How many triangles will I end up breaking it into if I triangulate it?
N-2.
N-2, okay, I think I believe that, but let's think of the convex polygon. Okay, here we have bunk, 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 okay, 1, 2, 3, and so I've got 4 polygons, 4 pieces, and I've got 1, 2, 3, 4, 5, 6 vertices, so it's N-2. Okay? How would I find the smallest number of convex pieces that I need? Okay? For this polygon, how many pieces, what's the smallest number of pieces I need to do to make this into a convex polygon?
1.
It's already a convex polygon, right? Do people understand the problem now? Okay? So how would I go about doing this? Okay? Yes?
Maybe because you said like the Van Gogh here, the triangulation was a tree.
Yeah?
You could do like a DSU algorithm to try to like join triangles and see if they, or join polygons and see if they're still convex when they're joined.
Okay, so that might be, okay, so you're saying take the tree and do something to look at the chunks of the polygons by the tree. One reason why I'm nervous about that is that we know that there's lots of different triangulations of something. There's an exponential number of triangulations. And it's not clear to me that the tree of any one triangulation has any special property. Okay? So I'm not going to immediately. How would I do this? I think I heard something that sounded interesting. Yeah.
If you have one internal angle larger than 180 degrees, you have to cut into pieces there.
It should be clear that if I have an internal angle that's greater than pi radians, okay, then this thing has to get cut, okay? So kind of when I've got a convex chain of things, everything is good, okay? Any questions about this? That's one level of do it. How would I try to find the minimum number of cuts?
You try to match one cut with more than 180 degrees with another one.
Okay, so you're saying, what I would really love to see is to find somebody who is another convex, what's my platonic dream of a thing to cut? You're saying if I can break up two convex things together. But maybe I can, maybe I can't, okay? How would I do this problem? How would I find, what is interesting about a polygon, okay? Polygons are ordered structures. The points go from one to dunt, to dunt, to dunt, to dunt. Okay, there's a chain, an ordering among them. How do you optimize things when you've got ordering on your structures? Okay. What algorithm and techniques do people use? I have a feeling I'm confusing you with what I'm asking, rather than I'm going to say something so amazing that you've never heard before. What is the technique that, to my mind, is used for finding an optimum of things over structures that are ordered? Dynamic programming. Okay? So what about doing dynamic programming here? Okay? What do I want to know? Okay, what am I going to stick a chord when I have a non-convex polygon? Again, my people polygon, whatever. Bunk, 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 bunk. What do I know? Okay, I'm going to try to figure out for every range of vertices from I to J, what is the smallest number of convex pieces, okay, that I can make from the chain from I to J after adding the chord IJ, okay? For some pairs of vertices, I can't add a chord. For some of them, I can. And does everybody see what happens when I add this chord, okay? If it wasn't a convex polygon before, okay, adding this chord, well, okay, what do I know? If I want to know the smallest number of pieces from this chord, what do I know? There had to be a place where there was an I and an X and a Y, such that there was the smallest number of ways, I know the smallest number of ways of breaking this up, and that the piece from I to this and J to this is convex. So I will claim that for all I and J, there are a certain legal number of chords that I can use to break this thing, that if I put this here, there's certain runs from here and runs from there, that if we had the previous chord over here, this would be convex. And if I know what the smallest number of pieces here is, I know that this is going to be one more than the smallest number of pieces you can make over all chords of this subrange. That would leave a convex piece when I have this here. Okay? Do people sort of see what the basic idea of I think my recurrence on the screen is wrong. Okay? Yes?
Can you explain again, please?
Okay, so what is the problem here? Suppose I want to know, let's say I have an open polygon. And let's say it looks like this. This is an open polygon from I to J. Can I compute what is the smallest number of convex pieces that are possible in this thing, given that I connect I and J? Okay? If I connect I and J, is it going to I claim, the number of convex pieces I get is gonna be one more than the number of convex pieces I had from over some other sub-range. This internal region had to have been bisected in some way. What chords could I have added before that would have left when I make this, would have left a convex polygon at the end? I could have added this one. I could have, let's say, added that one. Okay? I could have added this one. I couldn't have added this one. So I think these are the only three chords that if I have to use this, as I add this piece, that doing this, adding these chords, would leave a convex piece down here, right? Which is the optimal way to divide this thing into convex pieces? If I want to know the minimum number of pieces to carve up the chain from I to J, I consider over all chords that will leave a convex piece with the chord IJ. In this case, if I did it right, there's three others. What's the cost of it going to be? I guess this one would also have worked, excuse me, right? That one would also have been a legal thing to have added. And maybe this one. I haven't quite worked that out again. Those might be the legal chords that would leave it as convex. What is the optimal way to have, to end this thing and leave a convex piece? It is going to be the minimum, 1 plus the minimum over all of these legal chords of the number of convex pieces you have to divide up the remainder. That's what the idea of the recurrence is. Yes?
Couldn't you possibly need to add two chords in order to get the correct solution?
Well, if adding two chords, well, what does adding two chords mean exactly? Tell me what adding two chords means. Okay? I'm saying right now that if I can cut from I to J, I'm going to try to figure out what is the optimal solution using this chord. Remember, there's a rest of a polygon out here. Okay? What is the optimal solution from the smallest number of convex pieces I need on this piece of the polygon if I use chord IJ? That's what a M of IJ is going to be. The smallest number of convex pieces on the subchain from I to J, okay, if I add chord IJ. I'm going to do this for all possible chords eventually. If you're telling me, what if I need to use two chords? Well, there's going to be an outermost chord. I is going to get connected, if he said, as he said before, if it was a non-convex angle, then it's going to get connected to at least one other place, right? So what am I going to do for all possible chords? Okay, I am going to say that if I use this chord, what's the best way to use this chord? Well, it's going to have to create a convex piece in my neighborhood by growing a chain from here to here. There's going to be an end of that convex piece, perhaps over here. There's going to be an end of the convex piece, perhaps over here. That's because we added a chord here, and now this is my last convex piece. What's the cost of doing that? I create one new convex piece, and I want to know also the number of convex pieces the region from X to Y can be carved up into. And that I claim is being done recursively. That is being done by dynamic programming.
If I plus, if the chain from I to J is convex, then Mij is 0.
Then that's my initialization case, isn't it?
And then it would be 1 plus the sum of I to k and k to j.
So, in the special case of a convex polygon, what is the minimum? We agree that in a if we add this chain, we've added 1 and I guess created a convex piece. From here to here, it's 1 and we've created a convex piece. Here and here, we've created a convex piece. Okay? My claim is by adding any of these chords or not adding the chord. There's a special case of me adding my chord actually back at ij, where I and j are actually edges of the polygon. So I'm not sure I'm getting what your concern is. We agree that kind of the basis case is that a convex region is going to have require 0 cuts. Okay? And in general, once you add a chord, okay, if I add this chord, what is the number of the minimum way to triangulate this, to partition this thing into convex pieces without it? Well, there is going to be a previous cut. What is the consideration for that previous cut? Certainly, the edges of the polygon, the value of the previous cut, and this, either that is convex or it's not. If it is not convex, we're not going to allow that, not going to consider that case. But if it's convex, we get 1 new convex region, and we have to finish the job here, which is being done recursively. Yes?
So for every chord, you have to check for that whole segment it would be convex.
I'd have to check whether that segment is convex. I'd like to have to check to make sure that segment doesn't intersect any other point of the polygon, because I couldn't add a chord if there was something in there. But for all legal places where you can add a chord, it divides the polygon into smaller things. Dividing it into smaller things makes it gives you your recurrence, and that's the idea here. Any questions? How do people see the basic idea? Or no, questions?
Could you write the recurrence?
Could I write the recurrence correctly? That's actually what I think you would like me to do. I'm going to write it, but I don't think I'm going to write it in a way that makes you happy. Let me try this. I claim, again, let's say that my definition of what the recurrence means is correct. M sub ij is the minimum number, smallest number of convex pieces in the subchain from I to j, right? Now I'm going to say my recurrence is M sub ij is going to be equal to 1 plus the min over all legal xy of, okay, the min over all legal xy of the cost of going from, what you call it? M sub xy. I think this is what I think is what I want. Okay? Does this make sense now?
Yes.
Okay, so this is simpler than it was on there and more correct. Okay? What am I saying? For all legal chords that I'm inserting, legal means what? Means that from I to J, from I to X, from X to Y is one edge, and from Y to I means that this is a convex region. If adding XY leaves a convex region, it's a legal chord to consider. And then I will simply take the min, 1 plus the min of all of these possibilities.
And the complexity is n to the 4th
Okay, so what is the complexity, okay? As far as I'm concerned, the complexity in any dynamic program is the state times the cost of actually filling this thing, right? So what is this going to be? Well, that the state is n squared because there are two vertices on the boundary of the polygon, two vertices of the polygon. Here we're going to go through all legal chords. How many legal chords might there be from any polygon? Okay, from any point. Okay. I guess if the object was convex, IJ, how many legal chords are there? Well, any chord from here to here will leave this thing convex, right? So maybe that's where you're getting your n to the fourth from, right? Because there's up to n to the fourth, up to n squared chords that might be created, okay? All of which, that would be legal. Plus there's the time to test whether a chord is legal, okay? And that might add another factor of n times this, right? Because a chord is going to be legal if this thing is convex. How do you test whether this thing is convex? You see that all the internal angles that you get are less than pi radians, right? So this, I think, will definitely run an n to the fifth time, okay? But, and there may be some optimization that I can see here. Any questions?
I don't see how it works in a case when the polygon bifurcates into two paths, let's say like two tentacles. It looks like you need two.
Well, okay, so you're saying, what if my polygon is,
Yeah. And make them like bend in so they are concave by themselves.
Okay, I see. So what you're now worrying about is this.
Yeah.
That's actually an interesting case, okay? And this is a problem, okay? So if everybody's seen now, he's now got a problem, okay? That here, but now what do we know here? We know that this over here, we could conceivably solve recursively. The problem is here, my boundary is no longer one of constant complexity, okay? And so this is actually a case that suddenly I maybe shouldn't have started talking, okay? Any questions? It's good to see why, when you see an optimization of problem on a polygon, you should think dynamic programming, okay? That much is clear. Why might dynamic programming not work? And now here, maybe we've got an example of this. Is if the complexity of what my recurrence thing is not constant, okay? And that's what would happen here. Think about a polygon that looked like, you talk about many tentacles. Now, in adding this, am I going to create a convex region? It's going to depend upon how I connected this, and maybe this, okay? And now that's no longer a constant thing. So, okay, so let me walk backwards from here, okay? Let's say it's a good example, and it's an example the professor is sometimes wrong, okay? Any questions about that? Okay, good. Okay, so let's go to some other things and hope the professor is right, okay? And what I would like to do now is talk about a class of geometry problems that are, not a sort of general technique for solving geometry problems, okay? That are, that you can apply to a lot of different things. And it's the descendant of this algorithm we talked about, like the Grandstram where we sort things on X. A sweep line algorithm is an algorithm where we're going to process a bunch of geometric objects. Maybe they're points, maybe they're lines, maybe they're line segments, maybe they're polygons, maybe they're special cases of squares or whatever. And the way that we're going to process them is to walk from left to right over the geometric object. What's interesting about this? Let's say our geometric objects are line segments, which is what I've got over here. I will claim that as you walk from left to right over the geometric objects, only a small number of things can occur. One is you may occasionally encounter the left vertex of a line segment. So as we move from left to right, okay, sometimes we're going to have an event where a new vertex is introduced. Sometimes we're going to have an event where a segment disappears, okay? That's when at the end of a segment. And sometimes it's going to be other less easy to predict events based on what the input was. If you had a bunch of line segments given to you, okay? Finding the intersection points. Another event would be an intersection point. What is the idea of one of these sweep line algorithms? We're going to keep track of two different data structures. One is going to be what I'm going to call something to keep track of future events. That is going to be a priority queue or a sorted order in simple cases of it. But it's basically going to tell us what are the exciting things that come sorted in order from left to right. In the case of line segments, you're given initially the left endpoints, you're given then the right endpoints. Those you could put easily into a priority queue. You might also be interested in things like where the intersections are when they occur, okay? And so the reason I want to say you're going to use a priority queue to maintain the future instead of just a sorted order is for certain of these geometric problems, new events come along. The other data structure that you're going to need to keep track of is something I call a horizon data structure. It's going to maintain the order of the things we have by the y coordinate, okay, as they intersect our sweep line. So if you look at this particular illustration, from here to here we hit nothing. In this range till the next event we only hit A. In this range from here to there we have A above B. Then came C, we have A above B above C. If we look at this in our horizon, we have A above B and above C. Now, if we have lines, 3 lines, ordered by aboveness and slope, can you predict from here, let's say you're at this point, here you have these lines, where are the possible intersections that are going to come up next from this ordering of the lines? It could be that this and this line are going to intersect in the future. Why are they going to intersect? Might they intersect in the future? Well, they are pretty close to each other because they are in the same order on the horizon. And the slopes are different. So what could we do? These are a good candidate now. The moment that we first have 2 neighboring lines of different slopes, of different slope directions, we can look ahead and say, what is the intersection of that point going to be? And it makes sense. Does it make sense to try whether this line is going to intersect this line? It can intersect in the future because they are of diverging slope. Does everybody see that? So I don't have to worry about that. Do I have to worry about the fact that will this line ever intersect this line? Okay? Well, this line may or may not intersect this line. It has to do with the relative slopes that we have here. But if they're going to intersect, they're going to be neighbors of each other when they intersect. Notice that what's going to happen after we get past this point? The order of these two lines is going to reverse. And if this was A, B, C, now the lines are B, A, C. So what do I claim? All future intersections are going to come from neighboring lines, okay, in the order, and and an analysis of the slope. So the basic idea of a sweep line algorithm is that we maintain these structures as we go by. This is how you compute all the intersections of line segments, this kind of thing. Any questions about this, how the sweep line algorithm works? How many of you have ever implemented a sweep line algorithm in geometry? Many of you, most of you, I'm not surprised, okay? But what is the key idea here? There is an ordering of the objects with a priority queue, and there is a horizon data structure maintaining the ordering on the Y, okay? And this kind of an algorithm can be used for all kinds of different things. If you say, what is my main paradigm to try to figure out what is the intersection of boxes if I had them on the plane? What is the intersection, how do I find intersections of line segments? How do I find lots of things? The answer is you use these kind of sweep line algorithms. Any questions? I think the convex hull sweep line algorithm that I developed, okay, is a good paradigm of that. We had the points sorted by X. That was my X-ordered priority queue-like thing. Then there is the Y side. That wasn't quite so interesting, but it was necessary to maintain the chain of points, okay, in the order that they had appeared so far that was still on the active end of the hull. Any questions? Any questions about these arrangement things? So how would I find the area of intersection of two polygons? This is a good classic example of one where you would want to do a sweep line algorithm. What is the basic idea for this? If I'm going from left to right, okay, I am going to pass my line. What are the interesting events? The interesting events are going to be when new segments get created, new segments get destroyed because we have walked past them, the rightmost point, okay? What is going to be the interesting idea? When we are sweeping from left to right, what are we going to want to do? There is no area outside here. When we get to the first vertex, we now have two edges coming out of it. What is the area of the polygon? Well, it's the stuff between those two edges. We now have another polygon. That's the next leftmost point. The area in it, the horizon, is now at this point going to be the two green edges with the blue edges below it. Okay? What is the condition for an intersection? Well, it's a question of when one of the blue segments intersected one of the green segments. That's going to start an area where the next, of the point of intersection. And by partitioning this area of intersection into slabs, okay, marked by where the sweep line intersects the region as we go along, we can accumulate which parts of the area are in the intersection, which parts are not, and that's how you solve a problem like this. Any questions? I don't know if that's too fast or you've seen it before or something like that. But the plausibility is, if you have geometric objects from left to right, okay, you keep track of what you're doing as you walk across it. This is the basic paradigm for solving lots and lots of these problems. Any questions? Okay. That I believe. Let me show you one other piece of magic that is very, very useful with these sweep line algorithms. How many people know about duality? A few, less so. What is an interesting thing about points and lines? Suppose we have a point in 2 dimensions. What is the number of coordinates that we need? Here I've got a point. See this point, that red point? How many parameters does that red point, you need to specify that red point in the plane? You need 2. Why is that? Because it has an x coordinate and a y coordinate, right? What about a normal line? How many parameters does it take to specify what a line is? Okay, 2. It has a slope and an intercept. Does everybody agree that points have 2 parameters and lines have 2 parameters? Okay? Is there a way we can look and see and say that points are somehow the same as lines? Okay? They are both things with 2 parameters on them, right? What about if I do a transformation? Okay? Where I take a point ST and I map it to a line where the slope is going to be S and the intercept is going to be minus T. Does everybody see that by doing this, I can turn any point into a line? And by doing it the other way, any line into a point. Does everybody see I can do it? I mean, it should be clear I can do it. It may not be clear that there's any reason why I want to do it. Okay? What's interesting about this? Look at this example here. What do I have here? I have one blue line and 2 blue points on it. I have one black line with 2 black points on it. And I've got one red line, red point, that's at the intersection of the blue and the red line, right? If I do the dual on this, what should happen? How many lines should my dual have? I'm going to take every point and turn it to a line, and every line and turn it into a point. How many lines will I have in the dual of this thing? 5. 1, 2, 3, 4, 5. How many points will I have in the dual of this thing? 2. Ka-chunk, ka-chunk. Okay? Now, what's interesting about this? Okay? There are actually what do we know about this red point? The red point intersects 2 lines, right? It becomes a red line that intersects 2 points. What do you think those 2 points correspond to?
The lines.
The red, the blue, and the black line. Okay? This you have to see and test yourself to really convince yourself this is true. Okay? But this is kind of an amazing thing. Okay? It means that I can turn a problem on, in this case, let's say the problem was on lines, to a problem on points. Or I can turn a problem on points into a problem on lines. Okay? And sometimes this is a useful way to look at this thing. Okay? Any questions about this? This looks like this is new to a lot of people. Okay? And this is kind of a very, very useful trick if you can see it and understand it. Okay? Because it gives you another way to look at problems. Okay? Sometimes a geometric problem in this space can be converted into a geometric problem on that space such that they really are, that one of them you know how to solve. And if you know how to solve one of them, solve that one, and then just dualize the answer back. Any questions about that? The key point about this particular duality transformation is that whatever, like I said, if you had 2 points on a given line, that line is going to become a point with 2 lines going through it. Okay? And vice versa. Any questions about that? How much time does it take to give a set of n lines and n points to dualize it? How much time should that take? Or then you're just sort of taking every point and reinterpreting it. Okay? Now, of course, you're going to create lines maybe that have a lot of intersections when you had points before, but anyway, this gives you another way to look at the arrangement of points. What good is it? Okay? I'm going to claim that there are ways you can look at certain problems you have known, okay? And if you see them right in dual space, okay, they give you another problem you have known, okay? What is the convex hull problem? The convex hull problem, which you guys know now, is what? You're given a set of points, and what do you want to do? You want to find a bunch of lines, actually lines which have sides to them, an ordered line, okay? Such that all the other points lie on the same side of that, right? That's another way to think about what a convex hull is. A convex hull is going to be if you have points that go from I to I plus 1, such that all the points lie to the right of the line I plus 1. All the points lie to the right of the line I plus 1, I plus 2. All the points lie to the right of the line I plus 2 to I plus 3. Does everybody see that's what a convex hull is? Okay. And what do I know? The points are 2-dimensional. The lines that are being made from them are 2-dimensional. What does a convex hull look like in dual space? Every point became a line. Every line became a point. Okay? And this is going to be maybe not immediately obvious, but basically, when you do the duality transformation of these points, okay, the upper envelope of the convex hull, namely from here to here, is going to represent a convex region in dual space that's all on one side of the lines. The other piece is on the other side of those lines, okay? So there's kind of a connection here between the problem of finding the points on the convex hull as there is if I give you a bunch of half planes, directed lines, ka-chunk, 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 ka-chunk. What is the region that lies within all of those half planes? Okay, that's what we thought was interesting for linear programming. Okay, you could have built that in, maybe, by incrementally taking a polygon, adding another plane and cutting it off. Or if you understood duality deeply enough, you could find the convex hull and the convex hull of the duals of these lines. And that will tell you about what that region is that's being intersected. How many people sort of see what's going on? I don't expect people to. This now requires more thinking about what this actually means. But it should be clear that there is room to interpret, okay, things that were on points in terms of things that are within lines if you take this duality transformation. Any questions? Let me show you what I think is a simple enough example of this, though, that maybe you'll be able to really see the power of duality. Okay, to the point where maybe on something you can program it. So we talked about degeneracies as being weird things in the point. Points are in general positions if nothing weird happens. Now, what is a weird thing that happens to points? It could be that we have an arrangement of points where here we have 3 points and they are all perfectly on a line, right? That's not something we would normally like to have. If you have a random set of points, it's almost never going to be 3 points on a line, okay? Maybe, actually I guess if these were stars and in this hemisphere, I am told that you guys have 3 stars that are on a line. That's a Southern Cross, right? You guys have this kind of a situation? Okay, and I haven't seen the sky, it's never been not cloudy enough for me. But I'm told in this hemisphere, the constellation you see is a cross, right? The cross is interesting because there are 3 points on a line. Okay, as I understand it, don't take me for this thing. But do you see what I mean, what the problem is? Suppose I am giving you a set of points, and I want you to tell me, are there 3 points that lie perfectly on a line, on the same line? Okay? How might you do this? You see what my problem is? I'm giving you as input endpoints. Find me is there a line such that all 3 of them are on, that 3 of these points are on the same line? How would you do this? Yeah?
So if you could do it in quadratic time, you can take a single point and then measure the angles to all the other points.
Okay, so let's just think about it. First of all, it should be clear, in cubic time, how would you do this? You try every triple of points and see whether they're on the same line. Okay, so that I can do. And you're telling me you have a fancy quadratic time algorithm for it, right? Okay. Let me think of another algorithm problem. What if I have n lines, ka-chunk, maybe I'll get another marker. This may be brighter. Here I've got a line, ka-chunk, 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 ka-chunk. Suppose I want to know whether or not there exists 3 lines that are going through the same point. Okay? If I give you n lines, can anyone give me a cubic algorithm to tell me whether all 3 go through the same point? There's 3 lines that go through the same point, yeah?
Cubic or quadratic?
First, let's try cubic, just to make sure we're all in the game together.
Try every pair of lines.
Try every pair of lines. Try every pair of lines for cubic.
Yeah, but will be cubic.
You say it will be cubic. The way I would be doing cubic is by trying all triples of lines.
Of course. We will try every triple as well.
Okay.
Try every pair of lines, find the intersection, and now check if there's a 3rd line that also passes through this point.
Okay, so you're going to say pick 2 points, saying boom. I see. You take 2 points, you find their intersection, and now you ask for a 3rd, every other line. Does it go through that endpoint? Yeah. That would be an n-cubed algorithm for it. Okay? Now, if we're looking for a quadratic time algorithm, which of these problems sounds easier to you? Is it trying to test whether you've got endpoints at 3 points on a line, or 3 lines are going to go through a single point? Which of these is an easier problem to test, or easier to come up with an algorithm for, yeah? You think the first one is easier. Does anyone think the second one is easier? You think the second one is easier? I claim that they've got to be the same thing. These are exactly the same problem. Does everybody see it? One of them is wearing a a disguise, a costume, like for Carnival here, right? You guys have Carnival? I guess you wear costumes, right? These two problems are the exact same problem, okay? And which one you find easier is a question of taste. You in the back seem to have good taste, and you like the first one. You in the front have good taste, you like the second one. The point is, whichever one of these problems you find easier is the right way to solve both of them, okay? Any questions about that? Yes? Now you're saying, okay, what is the quadratic solution to the first problem? Okay? What is your quadratic solution to the first problem?
So for example, you could take for each point all the angle to all the other points.
For each point, okay, so now what do we have? A set of points. For each point, I'm going to find the set of angles to every other point, right?
With respect to the horizontal.
What?
Yeah, with respect to the horizontal.
With respect to the horizontal, so I'm going to find the angle, for this point, it's here, right? I'm going to find the angle to every other point. Boom, 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 boom.
And if there's two of those that are the same or that are 180 apart, then you have
Okay, if any two of these, so saying if this point is involved in a triple, what do we know? Its angles to any two of these points is going to be the same, right? And so now I think I understand what he's doing. There are n starting points. He's going to take the n, find these n angles. If this is involved with collinear with two other points, then those angles will be the exact same. So in linear time, he's going to find the largest, a collinear, if this point is involved on a line with two other points. And he's going to do that for all n points. N times n is n squared. Okay? Those of you who dealt with the line problem, does anybody have a favorite quadratic problem foretelling whether or not in the line problem there are three intersecting points? Yeah?
So take for each line, iterate for every other line and find the intersection point.
For each line, take every other point and find where it intersects. Ka-chunk, 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 ka-chunk.
Take every other line, see where it intersects, and if two of them have the same intersection point, then there are three lines that intersect at the same point.
Okay, so you're saying that if there are three, there's going to be two copies of the same thing.
Yes.
How do you tell whether there's two copies of the same thing?
You use some sort of data. Maybe you can.
You use some kind of data. Okay, this now is a little bit. You have to use some kind of data structure now, right?
Array. Put them in an array and you sort them by.
Okay, you sort them, but where did your quadratic time algorithm go?
Right.
Okay. Does everybody see that he's that? Okay, so I understand his algorithm as n squared log n.
Right.
Okay.
Isn't the other one the same because you have to find like two angles that are the same?
Okay, and wait, is that the same thing that's happening with him? He was saying, are the two angles the same? He's got the same problem over here. How would you solve that problem? Does everybody see that this is looking like n squared log n in the worst case now? How would you solve that problem?
an order set.
What?
An order set that has base data structure.
Okay, you're using some complicated data structure, it sounds like. I would say a hash table in practice might be a thing you would use, although the worst case didn't go away, right? Does everybody see that those are both n squared log n and both n, n log n, if you don't, they're n squared if you use something like hashing, and n log n, and n squared log n if you use a normal dictionary for this, okay? Any other questions? Yeah?
Won't the hash table have problems with the precision of the...
Will the hash table have problems with the precision? Well, now you're looking for exact duplicates here. What is going to be your solution for this one?
I win. I can compute intersections exactly using fractions.
Okay. So there's complicated. Okay.
I win.
He thinks he wins.
But can't you do the same with angles?
So that's still a lot.
Okay. Okay, let me tell you how I would do this. Okay, it should be clear. Neither of you is ultimately going to win because you're doing the exact same thing. Does everybody see you're solving the exact same problem?
Yeah.
Okay? You know, you're fighting about, oh, I had a solution, mine got past the judge. Mine got past the judge. No, but mine is better than yours. Okay? How would I do this, though? I wouldn't do it either way. You guys are doing it maybe more clever than I would. How would I do this?
Sweep line on the
Sweep line algorithm. This is what I know how to do. Okay? What would I be doing? I would say, is there a way to think of this as a sweep line problem, where I am given a set of points? Viewing it by a sweep line algorithm, if I want to find are there three collinear points, is it obvious what my sweep line algorithm is?
No.
Not to me, it's clear not. I can clearly hit every point and say, yeah, I'm here, I'm here, I'm here. But I've got these 3 points that are collinear out here, okay? I don't see that, right? But what about the case where I have lines? Does my sweep line algorithm now make sense to me?
Yeah.
Yes, my sweep line algorithm clearly works for the case of lines. What am I going to do? I've now got an arrangement of n lines. Okay? And I am going to do what? I'm going to start with my lines going out in infinity. They're going to be in a particular order. Does everybody agree? Once they're in a particular order, I'm going to be able to tell where are these two going to intersect. Right? I'm going to put that in my priority queue. I am then going to walk from left to right and adjust my horizon at every intersection point. Okay? And I'm going to ask myself, what is the case of 3 points, lines intersecting at a point? Well, my horizon data structure is going to tell me that these three, if they all intersect at this point, they are going to be next to each other in the horizon point thing, right? And I can now say, okay, these two intersect. If 3 intersect, then it had better be either the previous line or the line after it in the horizon structure. Does everybody kind of see that? So using my sweep, I can solve this problem, and I see how to solve this with my eyes, okay? And I know it's the same problem as the point problem. I don't see it with my eyes, okay? What is the time of doing this sweep line algorithm? Okay, let's think about that. What's happening with my sweep line algorithm? I've got n lines, they're going to intersect n squared places. I am going to have to maintain a priority queue of, of what these points are. Maintaining that priority queue is going to be log time per operation, or n squared log n. I'm also going to have to maintain my horizon structure. What happens at every step of my horizon structure? All the action is going to be between points that were, 2 lines that were neighbors. They're going to flip their order. Think about, remember, what's happening on the horizon data structure. I've got a bunch of lines. What happens after I cross this point of intersection?
Well,
All that happens is there is one local swap in the ordering of the lines. This can be maintained in constant time as I go through this. Does that make sense? I know what that vertex point was. I pulled it out from my priority queue. I now know where one of those lines is on. Those two lines are going to be neighbors in the horizon at this point. And they're going to flip afterwards. So in fact, it's a constant time operation there. So this is how I would be doing it. If I was smart, you say, give me that's 3 points in a line. I would say, oh, I can't sweep it, but I can dualize it. And if I dualize it, I can sweep it. And sweeping it is pretty simple and clear to me, okay? So if I could see that duality transform, I now understand how to do it. Any questions about that approach? Is that now clear? How many people understand what I'm talking about now? How many people don't and want to? If there's any questions, I'm happy to answer that. Yeah, any questions?
I don't have a question, but you asked if you.
Okay, you would like to. Okay, good. Okay. As far as explain it better, again, what's the important things to understand? There's two things I've talked about that are important to understand. One is to understand the consequences of this duality transformation and the fact that it turns lines that intersect through the same point into points that lie on the same line. Okay, that's the first part of this. And the other question is just to understand the idea of the sweep line algorithm. That we've got events happening as we go from left to right. We're storing those events in the priority queue, and we are maintaining the order of the Y objects as we go through and sweep this. Okay? Any questions about the sweep line stuff or anything like that? Any questions about this approach or anything like that? Okay, kabunk, kabunk, kabunk.
When you use a sweep line, is the complexity n squared log n?
The sweep line, in this case, had a complexity of n squared log n. Because there were n squared points, I stored it on a priority queue, my event thing. That was why it was n squared log n. Yes?
I have a question about the transformation between points. So
Yes.
Is it arbitrary the way I transform it, like st to sx minus c?
Okay, is it arbitrary the way I transform it? The answer is no. Suppose I translate every point and I transform it to 0, 0. I've made a transformation, right? What has that transformation done? It's lost every piece of information there was. That's not a good thing to do. This transformation happens to have the magic properties that it preserves this incidence relation. Okay? There may be other transformations that do, but this one does. And so that's the important thing. Not all transformations will preserve incidences. This one does. Okay? And so that is the clever thing about this duality transformation. Any questions? Any questions? Okay, I morally refuse to let you out 5 minutes early. So let me just give you one quick overview to a last part of the world of computational geometry, just so you're at least familiar with the terms. How many people have ever heard of a Voronoi diagram? Most people. Okay? What is a Voronoi diagram? A Voronoi diagram is for a set of points, carves up the terrain into regions around the points. Okay? Such that everything in this brown region over here, which is the nearest neighbor to that site, that vertex? I claim that this region, this brown region defined by the polygon, are the set of all the points that are closest to to this. Okay? Suppose these sites were where you have firehouses in the United States. Firehouses. I assume you guys, if something burns down here, somebody comes to go and put out the fire. Is that right? These people, I presume, live in a firehouse. Is that correct? They sit there with their equipment and wait for something to catch fire. What is the, you can see that I've got all of these, let's say all these points were firehouses. Suppose I go over here, ka-chunk. Which firehouse should catch the fire that's being caused by this laser beam? I claim it's got to be that firehouse, right? Because we've carved up this space into regions such that each region are all the points that are closest to each particular firehouse. Any questions about that? This kind of a diagram is called a Voronoi diagram, okay? And if you can build it, it's very, very good for answering closest point kind of problems, right? Suppose I give you a set of 2 points, only 2 points. How do you find the Voronoi diagram of 2 points? Suppose my points were kabunk and kabunk. How do you go and divide the plane up into regions so that they're closest to, we know which region it is, yeah?
You take the segments bisected.
You take the perpendicular bisector to this thing, right? You find the line between this, you take the perpendicular in the middle of it. Now everything up to here gets answered by firehouse A, and everything on this side gets by firehouse B. What happens if something on the line burns down? Which firehouse should answer it?
They can both.
They probably both look at each other because they don't know which one of them is closest and the house burns down, right? But you see that all of these are the points that are the same distance from them. So how do you build one of these Voronoi diagrams? It should be clear this Voronoi diagram is an interesting thing. It probably is clear that you could build it up in principle by looking at these bisectors between points, and that the Voronoi diagram is going to be made up of pieces of these bisectors between points. Okay? So one way that you could possibly think about building this thing is by looking at that and reasoning about it. Any questions about that? There is one other magic way to do this, which I'm just going to show you without actually telling you, without actually giving you the idea of how to do this. My claim is that if you take those set of points and you triangulate them, remember we may know how to make triangulations? See, there's a triangle, there's a triangle, there's a triangle, there's a triangle. My claim, if every 3 triangles that share every 3 points on a triangle will define a circle, right? That circle has a center. What does the center mean? It's equal distance to all the vertices, right? So the claim would be, if you have the right triangulation, and you now look at every triangle in the right triangulation, okay? The center point of that triangle defines a vertex of the Voronoi diagram. Okay? Does that seem semi-plausible?
Can you repeat it again?
What is the idea here? If you look at this, if you look at my diagram, you should see I have triangulated the points, right? How many circles pass through 3 points? If you have to have a circle that goes through 3 points, how many different circles go through it? 1. What if we now consider in that circle the center of that circle? My claim is the center of that circle has to be an equal distance from all 3 of those points. Right? That's what circles do. They be round and they have a center. Okay? So the other way to make these things is to find a very special triangulation and then use that to define the vertices of this as a dual. Okay? Does anyone know the name of that special triangulation? There's something called the Delaunay triangulation, which happens to have the property that it has the fattest possible triangles you can make over all triangulations. Okay? And the way that you get to it is if you have a triangulation and it's got skinny triangles, there's a way to, you can flip it, flip the edge between these two triangles that share an edge, and you will end up getting fatter triangles. So what's a way to build a Voronoi diagram? Go and triangulate it. Look for triangles that are not fat, because that if you flip the middle, it would get fatter. Keep flipping till you stop getting fatter, okay? And then you can use this kind of circular observation to construct the dual, okay? This requires more reason. You have to look at this to see that all this is going on. But that's kind of what's going on. Okay, any questions quickly? Okay. Okay, so that said, today's contest is on geometry. Good luck. I'd like to eat lunch with a different group of students.